Hi everybody, let's talk about carbonyls today. They are a special set of organic compounds with a special group which is having C double bond O. So let's talk about that today. So carbonyls are compounds containing the C double bond O group in them. That means the carbon atom has got a double bond towards the oxygen, and the oxygen is having two lone pairs on it. The carbon atom has then got two other valencies on it, and these valencies can be attached to different things. It may be attached to hydrogen atom on one side or both sides. It may be attached to an alkyl group or both alkyl groups, aryl groups, or even some other groups like O, R, and so on. And depending upon what they are attached to, we get different classes of carbonyl compounds. Then, about the bond C double bond O. This is a polar bond because of the electronegativity difference between carbon and oxygen. So basically, the carbon-oxygen bond has got partial positive character at the carbon and partial negative character at the oxygen. So this you can take it as being partially positive, and this you can take it as being partially negative. Therefore, reactions are very common in this bond. These are the common classes of carbonyl compounds. We have ketones, aldehydes, carboxylic acids, acid chlorides, esters, and amides. Now ketones are and aldehydes, they are similar because they have a C double bond O, and then on the two sides they have either an alkyl group or aryl group and hydrogen. There is no other element involved, ketones and aldehydes. Whereas carboxylic acids, acid chlorides, esters, and amides, all of them have the C double bond O in them. All of them have the C double bond O, and on one side they all have an alkyl group R, or maybe aryl group, or even maybe hydrogen. But on the other side, the other second valency on carbon will not be alkyl or aryl or hydrogen. It will be something else. Like for example, in the case of carboxylic acid, it's going to be an OH. In the case of ester, it's going to be an OR prime. Now consider the ketone here, which is having a carbonyl carbon and two alkyl groups on the two sides of the carbon. So, according to IUPAC system, we usually number the chain in such a way as to give the C double bond O the smallest number possible. But for our purpose in studying the reactions, there is another way of numbering these chains. That is, we number them in order of its position from the carbonyl carbon. The carbons adjacent to the carbonyl carbon, they are called alpha carbons. On either side of the carbon, they are called alpha carbons. The carbon next to the alpha carbon are called beta carbons. These are the beta carbons. The ones after that are called the gamma carbons. Then the one after that is called the delta carbon, which is not there on the other side. But this is a convenient way of numbering carbonyl compounds, so that when we refer to alpha, we immediately know that it is the carbon adjacent to the carbonyl carbon. In aldehydes, there is alkyl group maybe only on one side, so you still have alpha, beta, gamma on that side. In ketones, you are having on both sides, so you can number them as alpha, beta, gamma, delta, etc. on both sides of the carbon. Next, let's talk about the reactions at the carbonyl group. So there are two sets of reactions. One is reactions at the carbonyl group, C double bond O, which is actually nucleophilic acyl additions and nucleophilic acyl substitutions. The second set of reactions is the reactions at the alpha carbon to the carbonyl group. So let us see both of them separately. So reasons for reactions at the carbonyl carbon is because the C double bond O bond is polar and the carbon is partially positive. So it's like this. Carbon has got a partial positive charge and oxygen has got a partial negative charge. This is because of the electronegativity difference between carbon and oxygen. So because of this carbon being partially positive, nucleophiles can easily attack that carbon and form a new bond. At the same time, what happens is the double bond opens and O becomes fully negative, and it forms a tetrahedral intermediate in the process. So this is how it happens. A nucleophile attacking the carbonyl carbon, which is partially positive, and making a new bond here, which is this one. And then the double bond O opening and going to oxygen, so that oxygen is now negative. Then at this point, after the formation of the intermediate tetrahedral ion, two things can happen. Depending upon what type of carbonyl compound we are dealing with, two things can happen. The first thing that can happen is, if the carbonyl compound is an aldehyde or ketone, the negative oxygen gets protonated and it ends up as this product, which is actually an addition product. The double bond between the C and the O has been opened, and on the carbon a nucleophile attached, and on the oxygen a hydrogen, a proton attached. So this is nucleophilic acyl addition. This is shown by aldehydes and ketones. If the carbonyl compound is an acid, chloride, ester or amide, then the first step is still the same. The tetrahedral intermediate is formed, but after that the Z part of this acid, chloride, ester or amide, that is the part which is not the alkyl group, that means where it is chloride or the OR, ester group, or NH2, that part, it is a good leaving group, and so the lone pair, one lone pair of electron on oxygen will go back to being a double bond between the carbon and oxygen. So the double bond between carbon and oxygen is restored, and the group or atom which is Z, that is Cl or OR if it is an ester, or NH2, acidic or slightly acidic. So what happens is that this base will remove or extract this proton from this alpha carbon and make this an anion at this carbon. This lone pair can be delocalized to oxygen also. That means the ion formed by the base abstracting the proton is stabilized by resonance like this. So the resonance I can show you, it is like this. So this negative charge can move here. At the same time, this can move here. So this enolate ion formed by the base abstracting the proton can be stabilized by resonance, and that is why this is slightly acidic. The reason why the base is able to abstract the proton is because this stability of the conjugate base. So this hydrogen atom, that is the hydrogen atom on the alpha carbon, is slightly acidic, and the base extracted to form what is called an enolate ion. Now the enolate ion is a good nucleophile. It's a good nucleophile, and so it can undergo various reactions with many electrophilic species, giving new products. So here is the enolate anion, which can react with electrophiles. Various electrophiles are able to react with it like this, and a bond will be formed between the alpha carbon here and the electrophile. This is the reason for reaction at the alpha carbon, and this is how it takes place. So here are the three types of reactions in its overall form. The nucleophilic acyl addition, where you have the carbonyl compound reacting with a nucleophile. The nucleophile attacks the carbon and makes a new bond there, and this moves here, and then the negative oxygen takes up a proton and you get the final product. This is what happens in nucleophilic acyl addition. Then nucleophilic acyl substitution, here also the first step is the nucleophile attacking the carbon and making a new bond there, and this one moving here, and oxygen becomes negative. But in this case, the oxygen, which is negative, is not protonated, what happens is the Z will leave and the negative oxygen lone pair will go back and form the double bond once more. So that what you get as the product will still have the double bond on it, but instead of the Z there is a nucleophile. This is what happens during nucleophilic acyl substitutions. And then the last one, the reaction at the alpha carbon. Here there is a base which abstracts the alpha proton. So alpha carbons are this one and this one. From either of them it can abstract a proton. If there is a proton like this, it can be abstracted by the base to form the enolate. That means this carbon will become negative after the proton is abstracted, and this negative carbon can then react with the electrophile E plus to make a new bond at this point. So these are the overall forms of the three types of reactions at the carbonyl carbon.